5.5, properties of integrals and average value. So in this section, what we're going to be doing is, if I see from the first picture, if we have a function and our bounds are going to be going from negative a to a, and yes, this is supposed to be an a, that we see there's a symmetry about it. And it looks like, since they're both above the x-axis and it's a function that's even, so this is an even function. It has a symmetry across the y-axis that if I wanted to, and because it's going from negative a to a, it has a symmetry even there, that we can go ahead and say, well, really, we can evaluate the integral from 0, and I'm just rewriting what's here, and then of the function, and I can go ahead and just say, well, because it has a symmetry, it was even, we can just take 2 times that quantity. So I'm really only integrating from 0 to a and then doubling my area. But then if the function is odd, it has symmetry across the origin, which is this one, the second picture, we see we have an equal amount that looks like it should be below the x-axis, so a negative area, and above, which is positive, because it was an odd function. Notice the bounds are from negative a to a. And since that's the case, I would have this area, the first area, be subtracted from that, and it should then end up being 0. So if the function is odd and we go from negative a to a, it does end up being 0. So I'm going to go ahead and do a couple of examples. Number 9, we're going from negative 2 to 2 of the equation 3x to the 8th minus 2 dx. And this one, and we see that it's an even function. We should remember how to determine even and odd functions. Remember to determine, you replace x with a negative x, and if you can have the same function as a result, it's even. If you can factor out a -1, it's odd, and if you can't, it's neither. So in this case, I see that it's an even function. So then what I'm going to go ahead and do is I'm going to go and say, well, 2 times from 0 to 2 of this function, and now it becomes a slightly easier to evaluate. So we should end up getting at the end that our area is 1,000 over 3. Let's do 11. In this case, this function, which is from negative 2 to 2, of the function x to the 9th minus 3x to the 5th plus 2x squared minus 10 dx. And because I have a mix of odd and even exponents and a constant, I know right away, right off the bat, this is a neither odd or even. So if that's the case, well, I could just evaluate, but there might be a situation where I can break this up by our sum principle, that I can break these integrals up. If that's the case, I might find it easier. If I go from negative 2 to 2 and have the x to the 9th minus 3x to the 5th dx, that's completely an odd function. And then this whole integral is 0. And then I can say, well, plus from negative 2 to 2 of the 2x squared minus 10 dx, and this then is even. So I can go ahead and just make life a lot quicker and easier to evaluate that this first integral is going to be 0, and the second integral I can do 2 times from 0 to 2 of this function, and it has become much easier to evaluate. So from here, I know then my answer for the area should be negative 88 over 3. Let's go ahead and do another one that's with a trig function. Number 12, I have from negative pi over 2 to pi over 2 of 5 sine x dx. And if we remember our trig functions and how they graph, I know sine x is an odd function, and I don't even have to do any calculations. I know the area is going to be 0 because our bounds are from negative a to a, or negative pi over 2 to pi over 2. Same thing if I have an inverse situation. from negative 10 to 10 of the quantity x over the square root of 200 minus x squared dx. And in this case, this would graph as an odd function. And this is definitely going to be 0 also. So then if we move on, we have that we want to start taking average values. Average value of a function. We know, how do we find average values? You sum up the total and divide by the number of possibilities you have there. In this case, I'm going to be using that principle, but we're going to be using our intervals and how we want to divide up the interval. And in this case, because the average value, I'm looking at a rectangle, which we know is easier, but one rectangle rather than many rectangles under the curve. When I have from A to B this integral, and then you can see this purple area here that's shaded, the goal is that if the average is, we're going to have an equal amount under and over our curve using this rectangle of A to B. So then we're going to go ahead and we have this notation, which is a little bit difficult to see here. It's F bar, which is, they're saying is average. We're using that notation for average. And we're going to go ahead, and it's the same thing as we're having here. We can just go ahead and evaluate our integrals the way we've been doing. So for number 23, I have that the function is 1 over x squared plus 1 from negative 1 to 1 on our interval. So that if I want to go ahead and say the average value is going to be 1 over b minus a, and the integral from a to b of our function dx. So really our average value of this case is 1/2, and we can go ahead and integrate. But for this one, I'm going to leave as is. Maybe you could do the even and odd, make it easier, but I'm going to leave it. And I see it should be 1/2 the tangent inverse of x, evaluated from negative 1 to 1. And in this case, I get pi over 4. Let's do one more. I like this problem because of its applying to many situations. The function is x to the nth power, and we're going to be on the interval from 0 to 1. And it says, clarifying that it's a positive n. We're only doing positive n integers, so for our exponents. So if to find the average value of it, we have 1 over b minus a, the integral from a to b of x to the nth dx. And if we go ahead and take the antiderivative of this, and knowing our power rule, remember it's always x, add 1 to the exponent, divide by the new exponent. And then I'm going to evaluate it from 0 to 1. And from here, I can see when I plug in 1 for the exponent, I'm sorry, not for the exponent. For x, it should be 1 to the n plus 1 over the n plus 1. And 0 would make it 0, so I don't even need to do that second part of the FTC part 2. But then what about this notation? Since it's 1, my exponent, no matter what n I plug in, it's going to always be 1. 1 to any power is 1. So I can go ahead and rewrite this as just 1 over the n plus 1. And that is our answer for this situation, for the average value of this one. We're going to be going ahead, and I'm moving on to theorem 5.8, mean value theorem, but for integrals. And notice it's saying the continuous function on this closed interval exists for some point c in this interval such that it will be equal to the average value here. So the only difference between the previous picture and this one is now that there's some point C in here that has to be equal to this. This has to be equal to this. So the only difference in finding the mean value theorem in these kind of situations is we're going to be doing what we were just doing. So, and then we have one more step of finding C. So if I'm given the function 8 minus 2x and we're going to be going from 0 to 4. I'm going to find the average value of this integral. And I see that it comes down to this, or just 4. 4 is not my answer. 4 then helps me to go find this point C in the equation. So what I'm going to do is I'm going to take the original function now and have it equal to 4. The average value has to be equal to my function. I'm solving for x. I'm going to subtract 8 from both sides, and then I'm going to divide both sides by -2, which gives me x equals 2. So for this interval, the point that gives me the average value of the area on this function from 0 to 4 is when x equals 2. That would be where on the graph, that would be my C value. I can find where the average value would be.